Okay, so I will do the Pinbock duality. So with the linear duality, so if gamma is a group of linear transformation, then the dual group is just you can transpose inverse. So I don't think you need to put transpose, but I wrote it. Right, so open cone is dual. So another cone if So, so C star is a set of linear functional taking the positive value here. The C star is again a cone with origin. Of course, dual is itself. Okay, and the C must be properly convex, otherwise C0 cannot be one here. Okay, so if you want the two things to be open, right. Maybe I should say C star dual is zero is cannot be open. Okay. So if you want these both to be open, then you need these to be properly convex. Okay. So if not, then it's not going to be open. Okay. But of course, the this duality is still defined. So let's say gamma. Also, this dual group will act on C star, and the central dilatation extension by Z is given by adding scalar dilatation by S for the positive scalar numbers. And uh, so dual of some gamma prime. So if you have a central dilatation, you can do the same dual group, and this is a dilatational extension again. And the gamma prime is co-compact apparently PTC, so okay. Uh, so these are all the cases when they are properly convex. Okay, so I did say that. Okay, right. So C is properly convex, and so if you have a group in PGL and R, you can also get a dual group using the gamma star here, and taking the inverse image and so on. Okay, and RPN is defined as this. RPN star is a projectivization of RPN plus one dual. There should be no parentheses here. The properly convex open domain is dual to a properly convex domain. If it omega corresponds to convex open cone and C star to dual state. Okay, so then dual of this is itself, and gamma is dividing group if the central dilatation acts properly co-compactly on C with hostile quotient, and gamma is dividing if only C star is. So we can do this for Sn star. So Sn S of this is Rn plus one, the linear space with the projectivization double cover, and then uh, and then you can also define the cone and then another dual cone in the same way. And we still have these. And omega is a properly convex but not convex. Then omega star is a closure of a dual domain of omega star. Uh, right. And then here we can do augmented boundary, so which is xh, where x is in the boundary omega and h is oriented sharply supporting hyperspace here. And then you can, so instead of just the points, boundary point, you add these hyperspace meeting this boundary omega. So you enrich the boundary notion. Okay, so we can always define for some subset of A, you can define the inverse image, and then this is a sort of a quasi vibration. I don't want to go into deeply here. And So also there are some, so if omega 1 is a subset of omegas, these are two properly convex, and the dual one you can reverse equality. So right. So also if you have an independent subspace and then take a join and then take the dual, then you have to take the dual of it itself in respect to the subspace it is, and then you can take the join. Okay, so that's another sort of such things happening here. Okay, and so actually the duality will extend to this augmented boundary as well. So you have any xh, then you can send to hx by reversing. So because h will now be the boundary point. Okay, so if you have this was supporting them, so this is actually one-to-one map. Now, so the duality doesn't extend to the boundary as a one-to-one map, but this happens to be true. So, uh, right. So, there's this proper map sending xh to x, and if gamma x or properly on convex domain, then if dual does, and this is actually a duality map. Here is homeomorphism, and then the co-compactness here. So I don't want to get into that one, but uh, right. Yeah, and then here, so you can consider the C1 and strictly convex at a point if and only B star is C1 and strictly convex for a corresponding point at P star. So if it's strictly convex, then there is a unique point that corresponds to this point. Okay. Otherwise, if it's not strictly convex, then it may not be. Okay. If it's not C1, C1 is needed for there being unique point because there should be unique supporting point here. And if it's ellipsoid, dependent if omega star is ellipsoid, and so if you have some flat domain in the boundary, then that in the dual it will be some sort of a sharp cone associated with this subspace in the dual. Okay. So that's what we want to say. And what the Pinbock proved was that if you have a strongly tamed properly convex open cross orbifold, then dual orbifold actually is diffeomorphic to all. Okay, so this is called the Pinbock duality theorem. So this uses a Pinbock function, and then so Pinbock function gives you a strictly convex hypersurfaces. So you can for each point you can get a functional, so you can get a map to this thing. And also this extension also give you diffeomorphism here, but problem is that the circle, if you do it twice, you do it for DO and then DO start, so this may not be identity. So it's not an inverse map. So that's sort of a problem here. But uh, right. So the this Bimberg the duality morphism extend to the homeomorphism of the closure. But of course, we don't know it's really diffeomorphism. But even though if this is really smooth, when this is smooth, and this is equivariant respect to this duality map. Okay, so that's essentially by considering the switching things here. And also you can extend this to sweeping action, so it's a properly convex domain, and DG is compact. And the closure of this X properly, then the remaining metric, which is. So this is another thing I need for technically later. The So Bay also proved that if you have a sweeping action, then the dual group is also sweeping. So that's you use a Binberg diffeomorphism, which extend to this, and also this can be extended to you can also extend this duality for non-properly convex domains and so on. So I think I will skip that, but these all can be done for the non-properly because we all know these are just joins of spheres with subproperly convex set and so on. Okay, so you just need to understand these, and then there is a duality of properly convex sets, and so main thing is that if you have some sequence of properly convex domain converging to some compact convex set K, then the K star geometrically converges to compact convex set dual to K. Okay, so this doesn't necessarily need to be properly convex, but the point is, I mean, this holds for properly convex case. So when K and K0 are both properly convex, but it also holds for other cases as well. So that's the main theorem here. And this usually some results. Okay. And now I need to go to chapter 2. And this is just a survey of some previous results here. And so basically, so Wimberg studied this study of Cox's orbifolds um, and so Benoit generalized the work on prisms. Right, Katz and Wimberg were the first one to find some deformations of triangle groups. So this gave you some property, so which is not a quotient of hyperbolic space, and this was done with deforming these Cartan forms, and then we study some things here with the orderability, and my quiz studied on the truncation polytopes. And for compact hyperbolic streamline for Cooper and long and thesis rates produce many examples. So these are all numerical methods, but some of these are actually exact computations. Some very few, but mostly done by computers. And of course, we also proved some deformation space of complete hyperbolic Cox-Stokes before with or without ideal vertices. And so then we actually these are only with ideal or hyper-ideal vertices. So this is a bit wrong, sorry. So with or with ideal with only ideal or hyper-ideal vertices. And the Choi shows some weakly orderable Cox-Stokes before. So compact case has a is smooth with these dimensions. Okay. And then uh, and then we plan to do something here. And then Porty and Tillman they made theories with n-cell restrictive horospherical and made the study of compact hyperbolic ones to projective ones. Okay, so they and then they also did some deformation theory for parallel. So, but the different type of restriction on the end. So we are variant. Okay. So some examples are that so we have some polytope ridges codimension two side of P, and the P is three-dimensional edge ridges called an edge. And so we only want something of the edge associated with this angle. So if you have a hyperbolic polyhedron, then you want this to have angle pi but m divided by m for some positive integers, because you want to have an orbifold structures. So this will be considered projective as well. So Cox group is just some abstract group defined by these things where Nij is Nii is uh, symmetric is one, and then is bigger than two for I not equal to j. And of course, this maybe there might be missing pairs. Not all has to appear here. Okay, and so fundamental group of the OV4 will be a Cox group. So if you make this type of OV4, okay, and so these OV4 with is a polytope, and then given this sort of dihedral group action on the uh, I mean these faces are silver, then each ridge is given on order. And of course, the vertex, you also have to have a OV4 structure, right? So this is a bit wrong. So you need to have a vertices here as well. Okay. So some vertices could be missing, but anyway. So then the fundamental group will be this Coxeter group. Okay. And right. So P has a Coxeter OV4 structure. So if you could give that, and then so we will not study some product type ones, which are just polygon with product with identity interval and so on. And if it doesn't admit affine or cone type, which is just the polytope with vertex, and all the edges adjacent triangle has order 2. Okay, so then it's called p hat is normal type. Okay. Okay, so there's some previous mistake in my paper, so I think I should have removed the affine this affine type, but then I didn't. Okay, but so then everything is okay. Now we want to say the deformation space of a Coxeter fold to be all the projective structure quotient by isotopy groups. Okay, and so on, and then we want to restrict this to P. So restricted deformation spaces are the ones where the all the fundamental polyhedrotop is same up to projective automorphisms. Okay, so that's what we studied, and so in the orderable case, these things. So orderable means that for the three-dimensional case, that you can order the faces so that each side meets higher index ones in less than 3 edges, and if the OV4 is orderable, furthermore, if the set of order 2 edges and the edges of the higher order size. So if you take the union of those edges, that the cardinality is less than 3 edges. Okay. So for these, I think these are well, you can study these well. So if P is compact OV4, then I should say P hat here. Then this P is a truncation polytope. So this means that you try with the tetrahedron and you cut off the vertices, and you cut off the vertices again and again, and that kind of thing. Then you can compute the dimension here. Okay, and so for the orderable case, then we can also show that restricted deformation space has a smooth and then has dimension like this. And then yeah, so also for the three-dimensional hyperbolic polyhedron whose diagonal is all equal to pi and given a Coxeter OV4, then you can also show that this is a smooth dimensional manifold. So in this case, we don't have any finite vertices. We only have infinite ideal vertices. Okay, and then we actually generalize this to cases pi over p, p bigger than or equal to 3, and then only has a hyper-ideal or ideal vertices. Then this is still true. Okay, so this dimension is. Okay, and then also we do the vertex order. Okay, so this is what we'll be doing later. So I will skip that. Okay. Uh, and then Lee did lots of examples with cubes, and so just by some computation with Mathematica and finding Grosvenor basis, you can find lots of these dimension of lots of these spaces. And okay, so that's and other results are work of Hosono and Porti. So they usually work with the hyperbolic manifolds. Then the so this hyperbolic manifold has holonomy to PS so 3 ones and then go to PGR4. So it's called infinity projective rigid if the H1 is 0. Okay. So this is a add group X on this SL4R because this is a D group of this. Okay, so this means that you cannot deform this. So this is the first obstruction to deforming. So if it's 0, then you cannot deform. Okay, so it means rigid, and so they consider a case with the boundary uses union of tori, and the interior is hyperbolic with the complete hyperbolic with the finite volume. Then I should say it's complete hyperbolic. Sorry. And then it's infinitesimally projectively rigid with respect to cos if this induces this is injective map. So of course, this goes into this. I mean, I should say, right, this is pi one of boundary M. Okay. Okay. Right. So I mean, I could say I could drop M pi one here both, but because it's homology, but anyway, so there's some mistake here. But anyway, so partial M goes to M, but so in the cohomology, it goes in the reverse direction. So usually this is a bigger space. So if this is a injective map, then you call this infinite projective rigid. So which means that you cannot deform unless you deform this. Okay, so you have to so whatever deformation here, it has to be realized here. Okay, so if you put the boundary rigid, then it cannot deform. That's what this is saying. Okay, right. So Hosna Podis show that if you have orientable manifold is complete hyperbolic with the manipolium. If it's projectively rigid, then the infinitely many Dane fillings of M are projectively rigid. So in the hyperbolic manifold, if you have a cos, you can do infinitely many Dane fillings, which is given by a pair of prime integers. Okay, so for that, except for finitely many, you can do Dane surgery and still has a hyperbolic structure. So those things cannot be deformed. Okay, so that's what this is saying, and so again, yeah. So this one says if at least one Dane filling is satisfy this property, then the infinity many of them are like that. Okay. So for example, something like 1/k Dane fillings of figure 8 is projectively rigid, and some like this. And then the ballast did some work on these. And then the finite volume strictly convex projectively orbifold with ends. And so here you prove that they prove that if you have some projectively orbifold and subgroup is contained in less than so if you look at all the loops with the base that x with length epsilon less than m, then it's virtually nilpotent. So this is a generalization of Margulis lemma for the hyperbolic manifolds. So I did this for the dimension 2, and then they did it for the higher dimensions. Okay, and okay, so they also generalize this to Hitchin component here as well. And so each strictly convex projective operator is a finite volume is horospherical. So so if you have a strictly convex and then has a finite volume, then it's the N has a horospherical structure. Okay, and okay, so the final result is that the M is properly convex with the finite volume whose interior is holonomy is topologically parabolic. Then omega is strictly convex and is C1. So this is converse to this, so that if you have finite volume and uh, it's and then holonomy is topologically parabolic, then the being strictly convex and the C1 is equivalent. Okay, so that's what they prove. Okay, so these are some surveys of the result, and then I will go to the chapter 3 next time. So I end the lecture today here.